Hey guys, welcome to this video. So in this video, I would like to discuss a very interesting idea. Again, bits of which I have touched upon in many of my previous videos. But in this video, I want to try to put it all together into a coherent narrative, and I think you'll find this interesting. So there is something called like information in context of physics, and in this video, I would like to discuss what's the relation between entropy and information. So information has links with not just entropy as in statistical mechanics but also quantum mechanics. Since in quantum mechanics we have something called the postulate of unitarity or the principle of unitarity, which means that time symmetry is respected in quantum mechanics. I mean, by the laws of quantum mechanics, if you replace t with minus t in the laws of quantum mechanics, nothing would change. Physically, the physics would still remain the same, and that means uh, in context of quantum mechanics, it's possible if to go, the probability of event going from event A to B is the same as the reverse probability of coming from event B to A. And you can also think of it like this: that whenever a quantum system evolves, its evolution is governed by a unitary operator or a unitary matrix. This means that in less technical terms, this means it's possible to retrieve all the information about the quantum system. I mean, as during the evolution of a quantum system from a state from an initial state to a final state, no information is lost. That is the implication of this. So that's what quantum mechanics says. But on the other hand, if we think about entropy and statistical mechanics and the second law of thermodynamics, we clearly see that this does not hold. For instance, the probability of a state of a system evolving from a low entropy state to high entropy state is clearly more, because we do not see the reverse occurring in nature. We do not see disorder decreasing on its own for a closed isolated system. We do not see entropy decrease on its own. Locally, that can happen for an open system, provided the entropy of the system plus surroundings increase. So that is about statistical mechanics. Yeah, so sorry for the interruption. So the next point I would like to discuss, and that is the main focus, primary focus of this video, is the relation between the entropy and information. So quantum mechanics says that information is always preserved, fine, but we do not observe this behavior in our day-to-day life. When, for instance, the entropy of a closed system tends to increase, the overall entropy of the universe tends to increase, it cannot decrease. So the probability of A to B is not equal to probability of B to A in general, in day-to-day life, what we observe in statistical mechanics, entropy, whatever. So things do not seem to hold up. What changes? For one atom in the quantum realm, this holds, but when we talk about macroscopic systems made of billions of atoms, suddenly this does not hold anymore, this time symmetry or the information, whatever. Now, this is a very delicate topic. So what is information? Information can be understood in many different ways. For instance, I have already made a very long video about it, a lecture kind of video on which I write on the whiteboard and all. You can check it out. There I've actually explained the mathematics of information, a little bit of Shannon's entropy and all these things. I'll not go into those here because this is, see, right now I'm on holidays. I'm on a solo trip, and as you can see, this place is called Lama Hata. It's a place near Sitong, which is a village in the Darjeeling district, a kind of a hill station. Very good place for a short 3 or 4 days trip. So yeah, there will be disturbance. I mean, this is not a kind of place where to make videos, make technical videos. But yeah, I just want to discuss this with you because I will not get this natural setting, this background back home. So yeah, now information is, it might appear that more the entropy of a system, more the information. For instance, if a system has very low entropy, everything is perfectly ordered. So for instance, you consider a very ordered arrangement, then you don't need to really, you just need to specify the order, and maybe then you need very less information to describe the complete system. But if the system is disordered, it's just random, then you have to explain each and every aspect of the system. Otherwise you cannot, otherwise what you say will not be able to describe the system completely, describe all the aspects of the system. So it appears like as the system becomes more random, as its entropy increases, we need more information to describe the system. That makes sense, that is true. But up to a certain point, this does not mean that as entropy will go on increasing, the information will also go on increasing, because again, information has to be conserved. Indefinite increase in entropy doesn't really sound it sounds really at odds with the quantum principle of unitarity, right? So it's not like, see, it's very important to understand this very delicate balance. Let's consider two states, like a cup which is kept on the table. It's a low entropy state. The information, you need very less information. You can just describe the cup, but now the cup falls from the table and breaks. So you need to describe the complete state of the cup, of the broken cup. You have to tell me the shape, the size, the configuration, the position, the location, the orientation of each and every broken part. So you need more information. Entropy increases, information increases. But yeah, the relation between entropy and information is not that straightforward. Like entropy increases, information increases, blah blah blah. No, because this cannot go on forever. Let's understand why. And this behavior is observed, for instance, if you, this is just for those who know, I will not go deep into this here. For those of you who have studied the black hole information paradox, there is something called the page curve, the entanglement entropy versus the time curve. It was first proposed by Don Page. And entanglement entropy is basically the measure of entanglement between the information within the black hole and the information of the particles that fell in the black hole that is currently outside the black hole, that is contained in the radiation coming from the black hole, Hawking radiation basically, first proposed by Stephen Hawking. So that is entanglement entropy. And time means the lifetime of the black hole. The black hole forms at this instant, we consider from that time, and then till the black hole evaporates away completely. The time is the lifetime of the black hole. So then we see this entanglement entropy versus time. The curve is like this. It's a like this. It's a downward parabola. So initially information increase, this entanglement entropy increases and then it decreases, and it reaches a peak somewhere in the middle. So I'll not go into black holes here, but yeah, the idea is that why is this? You see, I'm not talking about any talking from the point of view of black holes specifically, because that will make things even more complicated. But you can understand it very simply also. For instance, if you consider the highest entropy state, that means the state which is in perfect equilibrium, the most disordered random state, like for instance, if we go by the prediction of Big Freeze, then as the universe is expanding and cooling down, its entropy is increasing. It will reach a state when every part of the universe will be in thermal equilibrium with every other part. That means no change can occur in the universe, no energy can flow between the different parts of the universe, no temperature fluctuation, nothing. The universe will be just a uniform, like nothing will exist. That is the highest entropy state, and technically going by entropy, that is the maximum entropy state. And that is disordered in the sense that it's random everywhere. There is no specific local order. You cannot distinguish one point from the other. In that sense, it is the maximum entropy state. But think of it like this: do you really need a huge amount of information to describe that state? Don't you need more information to describe the current evolution of the universe? So technically, you don't need a lot of information to describe that maximum entropy state. Of course, it has, for instance, you can think of it like this: you have a state which is nothingness. There is nothing before everything, like nothing, no particles, nothing. So you need no information to describe that state, minimum amount of information. Then you have a state which is entirely random, like there are a lot of particles which are just, but it's the same at every point in space, and it does not, as an entity, does not change with time. And if you look that way, if you look this way, it's the same in all directions as well. So that means assume excluding the information of the constituent particles. I mean, you have to say that this system is made up of so many huge number of particles, but excluding the specific information or the description of a particle, the constituent particles, you again don't need a lot of information, because it's the same everywhere. You don't need a lot of information because it's the same everywhere. You need a maximum information. The information is maximum somewhere in between, as the system evolves from its lowest entropy to the highest entropy state. For instance, we are very complex creatures, and the world around us is very complex. None of this would be were there in the Big Bang, and none of this will be there once the universe reaches that maximum entropy state as well. So that's why you can see why the curve is like this. The information is maximum somewhere in the between. So when we're plotting the entanglement entropy as a function of time, we essentially, you can think of it like this, though I'm not talking about black holes in general in specifically about black holes in this video, is that the information we are plotting against time, then the curve will be like this. And this you can qualitatively, you can see why information is preserved. The total information at the beginning of the process was very minimum, let's say 0, and at the end it comes back to 0. No information is lost or added or whatever in the process. But entropy will always increase. So I think that's what I tried to do in this video, just give you a very brief idea about this. And I hope I have talked about similar things in some of my previous videos as well. So if you have watched those, no point in watching this again. But otherwise, and it's a very beautiful place as well, as you can see. So I think that's all. I need to climb a long way down right now. So thank you so much for watching.